You step out into a 20 degrees Fahrenheit dawn wearing a $500 Gore-Tex parka breathable membrane, synthetic insulation, hydrophobic treatments, and almost immediately the doubts begin. The shoulders stay dry at first, but as you move, sweat builds against your skin. The wind finds seams you didn't know existed. When you pause to catch your breath, the cold presses in deeper, faster, turning that trapped moisture into a quiet thief of heat. Now picture the same landscape 200 years earlier, the upper Missouri in the winter of 1804 through 1805, where temperatures plunged to 45 degrees Fahrenheit night after night. The men of the Lewis and Clark expedition, wrapped primarily in brain-tanned buckskin shirts, leggings, and moccasins, often over a simple wool blanket coat or linen shirt, spent months outdoors. They hunted in blizzards, hauled wood through deep snow, repaired gear by open fires. Frostbite claimed toes and fingers despite their efforts, yet they endured sustained exposure that would overwhelm most modern setups. Mountain men like Jim Bridger would later push deeper into the Rockies, living year-round in buckskin through winters just as severe, sleeping on the ground under buffalo robes when they had them, or simply under the stars when they did not. This isn't a story of superhuman toughness. The difference lies in the system itself. Frontier buckskin clothing wasn't built for brief bursts of cold followed by a heated cabin or car. It was engineered for prolonged immersion in wet, windy, sub-zero conditions where sweat was inevitable. Open fires, the only heat source, and failure meant freezing long before rescue arrived. Today we accept that advanced materials must outperform anything from the past. Yet when conditions turn truly extreme and sustained, that confidence often proves fragile. To see why buckskin succeeded where many modern jackets falter, we need to move beyond comparing thickness or fill power and examine how heat, moisture, and movement actually behave when the margin for error disappears. Cold rarely defeats you directly. Moisture does. In sub-zero conditions, the most dangerous heat loss doesn't come from wind or thin insulation alone. It comes from what happens inside your clothing once you start moving. Your body produces heat roughly 100 watts at rest, climbing to 500 or more during hard exertion. And with that heat comes moisture, water vapor driven outward from your skin by the temperature gradient, at rates that can exceed a liter per hour in intense activity. Modern jackets are built to stop the outside from getting in. Membranes block wind. Coatings repel rain. Synthetic insulation promises warmth even when damp. On paper, it looks like progress. In practice, it creates a trap. As your body heats up during movement, sweat vapor pushes outward. Breathable membranes allow some passage. But in cold air, the vapor quickly hits the dew point inside the colder layers of the jacket. It condenses, not always visibly on the surface, but deep within the insulation fill. The jacket doesn't feel soaked at first. It just grows heavier, colder, less responsive. Once the synthetic fill holds liquid water, often 20–40% of its weight in real-world tests, the loft begins to collapse. Air pockets, the true insulators, compress or fill with conductive water. Heat loss accelerates dramatically. Field observations and mannequin studies show wet synthetic insulation can lose 40–60% of its thermal resistance, turning a jacket rated for -20 degrees Fahrenheit into something far less capable. When you stop moving, the moisture you generated during effort continues pulling warmth from your core, sometimes faster than the environment itself. This post-exertion chill is a pattern seen repeatedly in cold weather incidents. The body cools rapidly once activity ceases, and internal condensation amplifies evaporative loss. In sustained cold, this failure compounds. Wind strips remaining heat through the now damp shell. Melting snow wicks inward and refreezes. The jacket effectively requires constant movement or external energy to remain functional. Without it, warmth collapses. Frontier travelers lived in this reality every day. Long-distance snowshoeing, chopping firewood for hours, hauling trap lines through deep powder sweating was unavoidable. Yet retreat to heated shelter was rarely an option. During the Lewis and Clark expedition's winter at Fort Mandan in 1805, temperatures dropped to -45 degrees Fahrenheit repeatedly. The men spent months outdoors in brain-tanned buckskin garments, sewing hundreds of moccasins and leather items as cloth wore out. Mountain men like Jim Bridger followed, living year-round in the Rockies through similar extremes. Relying on the same material, their clothing systems assumed moisture would happen and were designed to survive it. Brain-tanned buckskin, soft suede from deerskin, processed with emulsified oils and smoked, behaves differently. Its open, porous fiber structure allows vapor to pass through freely while trapping millions of tiny air pockets for insulation. When wet from sweat or snow, it doesn't collapse. The collagen matrix holds loft, and the smoking process adds water repellency that causes moisture to bead or wick away rather than soak in. Fringe, a deliberate feature on many frontier garments, channels water outward and speeds drying often by an open campfire, where buckskin regains softness quickly without stiffening. Modern jackets often assume the opposite: short exposure, controlled interiors, and easy retreat to warmth. That assumption works in predictable conditions. In true sustained cold, where moisture is inevitable and drying opportunities limited, it doesn't take long for the gap to appear. Cold injuries rarely happen during peak movement. They happen during transitions when exertion drops and heat production falls. During steady travel, human metabolic output can reach 400 to 600 watts. The moment movement slows, output can drop below 150 watts in minutes. Clothing systems that depend on high heat input fail hardest at that point. Modern cold weather jackets are optimized for peak insulation under controlled conditions. Synthetic fills perform best when dry and uncompressed. In real use, they accumulate internal moisture during exertion and lose loft under pack straps, bending joints, and body weight. Laboratory and field tests show that compressing synthetic insulation by just 50% can reduce its insulating value by more than 30%, creating cold bridges at the shoulders, hips, and knees, exactly where circulation is already reduced in cold environments. Buckskin operates under a different principle. Brain-tanned deerskin insulates through a porous collagen fiber matrix rather than loft height alone. Even when compressed by kneeling, sitting, or pack loads, the fiber network maintains air spaces and resists total collapse. When damp, it remains flexible and vapor open, allowing moisture to continue diffusing outward instead of condensing inward. This matters during real frontier work. Trappers and hunters didn't move continuously. They walked for hours, then stopped abruptly to reset traps, butcher animals, or build camp. In these moments, clothing had to slow heat loss without requiring immediate shelter. Buckskin's gradual thermal decay allowed body temperature to fall slowly instead of collapsing all at once. Airflow behavior also differed. Buckskin reduces wind speed rather than fully sealing it out. This lowers convective heat loss, while avoiding the pressure differentials that force moisture back toward the skin. Modern windproof shells often block airflow entirely, increasing internal condensation and accelerating post-movement cooling. The result is a different failure curve. Modern jackets perform well at peak output and fail sharply when activity stops. Buckskin performs consistently across changing metabolic states. It does not maximize insulation on paper, it preserves usable warmth across time. Frontier clothing wasn't designed to keep people comfortable while standing still. It was designed to keep them alive while heat production rose and fell repeatedly, day after day, without catastrophic failure. Frontier clothing was not a rigid three-layer system in the modern sense. It was modular, task-driven, and built around one assumption: you will sweat and you will get wet. The layer worn closest to the skin was typically linen or light wool. This base layer was not meant to insulate. Its function was moisture, buffering, and hygiene. Linen fibers can absorb up to 20% of their weight in moisture without feeling wet, while remaining highly vapor-permeable properties confirmed in textile analyses where linen's hollow structure wicks sweat efficiently, often outperforming cotton in evaporation rates by 30–50%. This allowed sweat to move away from the skin before it could condense deeper in the system. Because linen and light wool were washable, they protected the more valuable outer layers from oils and salt buildup that degrade insulation over time. During the Lewis and Clark expedition in 1804, 1805, for instance, The men started with linen shirts, but increasingly relied on them as underlayers as their cloth deteriorated in the wet, cold conditions of the Pacific Northwest, where they noted rotting fabrics after prolonged rain. The primary insulating layer was buckskin. A single brain-tan deerskin shirt and leggings added measurable thermal resistance. Modern tests on similar tanned hides show thermal conductivity values around 0.15, 0.2 WMK, comparable to midweight wool while remaining breathable. When doubled, common in winter travel, as seen in mountain men like Jim Bridger who layered buckskin frocks over wool during Rocky Mountain treks. The system increased insulation without sealing vapor. Unlike synthetic midlayers, which depend on loft height and can lose up to 40% of thermal resistance when compressed, buckskin maintained insulation, even when compressed by movement, kneeling, or pack loads, due to its durable collagen fiber matrix that resists collapse. For extreme cold, an outer layer was added: wool capotes, buffalo robes, or fur garments. These layers were used selectively, not constantly. Buffalo robes, in particular, provided very high insulation values. Modern testing of comparable fur shows CLO values exceeding 4, far surpassing a typical modern synthetic jacket's 1-2 CLO, but were often removed during movement to prevent overheating and moisture saturation, as documented in fur trade accounts from the 1820, where trappers shed robes while snowshoeing to avoid internal condensation. Alfred Jacob Miller's 1830 seconds. Sketches of mountain men depict these robes draped over fringed buckskin, illustrating the modular approach in sub-zero conditions. Crucially, none of these layers formed a vapor barrier. Air and moisture could move outward continuously. Gaps were sealed mechanically instead. Overlapping sleeves and mittens, high moccasins or leggings, long shirts extending below the waist, and integrated hoods or collars. This reduced convective heat loss without trapping vapor, a practice evident in the expedition's journals, where they sewed over 350 pairs of moccasins and elkskin capes to seal drafts during -45 degrees Fahrenheit winters at Fort Mandan. Fringe, often dismissed as decorative, served a practical role. By breaking surface tension, it encouraged water to drip away from seams and edges, reducing soak-through and speeding drying, a feature noted in historical reenactments and analyses of 19th-century garments, where fringed buckskin dried 20–30% faster near campfires than unfringed leather. In freezing conditions, this limited ice buildup on garments and joints. The result was a system that adjusted insulation by adding or removing mass, not by sealing the body inside it. Heat loss increased gradually, not abruptly. Moisture moved outward instead of inward. And failure, when it came, was slow enough to respond to, as fur trappers survived multi-day blizzards in the Rockies by layering dynamically, without the rapid chill seen in vapor-trapped modern gear. Modern layering systems prioritize immediate comfort and peak insulation ratings. Frontier layering prioritized predictability under sustained exposure. That difference is why one system tolerated moisture and the other quietly fails when conditions stop being controlled. Cold weather clothing doesn't fail in theory. It fails in contact with fire, snow, compression, and repair limits. Frontier clothing was designed around open flame as a constant. Campfires were used daily for cooking, drying, tanning, and heat. Sparks were unavoidable. Clothing had to survive direct exposure without catastrophic damage. Buckskin does. Brain-tanned deerskin chars when exposed to embers, but does not melt or drip. The ignition temperature of leather is significantly higher than most synthetic fibers, and when damaged, buckskin degrades locally rather than structurally. A spark produces a scorch mark, not a hole that propagates. Insulation performance around the damaged area remains intact. Modern synthetic shells and insulation fail differently. Nylon and polyester soften and melt at temperatures between roughly 160–260 degrees Celsius. Contact with a single ember can create a melted hole that spreads under tension. Worse, molten synthetic material can adhere to skin, causing deep burns. This is why modern outdoor safety guidelines explicitly warn against wearing synthetic outer layers near open fires in cold conditions. Buckskin also tolerates drying while worn. When damp from sweat or snow, it can be dried gradually by body heat or near a fire without stiffening or cracking. Chrome-tanned leather hardens when dried improperly. Synthetic insulation, once wetted and heat-damaged, permanently loses loft. Buckskin recovers. Durability mattered because frontier garments were not disposable. A buckskin shirt or pair of leggings could last years. When damaged, it could be repaired with sinew or rawhide lacing, using simple tools. The thermal system remained functional after repair. Modern jackets rely on laminated fabrics, bonded baffles, and sealed membranes. Once compromised, their performance drops sharply, and field repair rarely restores insulation or vapor control. There is also a cold fracture issue. Many synthetic fabrics become brittle at extreme low temperatures, increasing tear risk under stress. Buckskin remains flexible well below freezing because its collagen fiber network does not crystallize or stiffen the way polymer chains can. In real frontier conditions, fire, snow, abrasion, compression, and repeated drying, buckskin failed slowly and locally. Modern systems tend to fail suddenly and globally. One melted panel, one soaked insulation layer, one torn membrane is enough to collapse performance across the entire garment. Frontier clothing wasn't optimized for laboratory ratings. It was optimized for abuse. And in sustained sub-zero environments, survivability under abuse mattered more than peak insulation numbers. Buckskin didn't disappear because it stopped working. It disappeared because it was slow. Producing a single set of brain-tanned buckskin clothing required weeks of labor, often several days to multiple weeks per hide, with accounts from traditional tanners describing 3-10 days of intensive scraping, braining, stretching, and smoking for one deer skin. A deer hide had to be fleshed, dehaired, softened repeatedly with emulsified brains or oils, stretched continuously by hand, and then smoked over wood to stabilize the fibers and add water resistance. The process demanded skill, time, and constant attention. Each garment represented dozens to hundreds of labor hours and years of accumulated knowledge passed down through indigenous and frontier practices. This handcrafting suited small-scale, self-reliant life in the early 19th century Rockies, where mountain men like those in the Lewis and Clark expedition or the fur trade era routinely dressed hides themselves as factory cloth wore out. Industrial clothing reversed those incentives. By the mid-19th century, factory weaving and mechanized spinning allowed cotton garments to be produced in hours instead of weeks. The cotton gin, invented in 1794, slashed processing time, enabling U.S. cotton output to explode from negligible levels to over 4 million bales annually by 1860. Cotton was cheaper not because it performed better in cold, wet. Cotton loses nearly all insulation, but because it scaled massively through plantation labor and mills. Raw cotton prices dropped dramatically, with a pound falling to around 10 cents by 1860 pre-war levels, while textile production costs plummeted as British and American factories churned out cloth at fractions of handmade rates. The fur trade itself collapsed in the 1840s, partly from shifting fashions. Silk replaced beaver felt hats and overtrapping, making wild hides scarcer and factory textiles more accessible via trading posts. Synthetic fibers later accelerated this trend even further. Nylon emerged in 1938, 1939, polyester in the 1940, and acrylics in the 1950s, allowing insulation and shells to be mass-produced with unskilled labor and predictable margins. A single factory could output thousands of yards daily, versus one hide per weeks-long effort. At the same time, energy became cheap. Coal in the mid-19th century, then abundant oil and natural gas in the early 20th, fundamentally changed the risk equation. Central heating spread. Coal stoves in the 1800s gave way to gas and oil furnaces by the mid-20th century, making indoor temperatures reliable for pennies per day in many homes. When buildings could be heated continuously for low-cost U.S. residential energy prices remained affordable through the post-war boom. Clothing no longer had to survive extended exposure without backup. Failure became inconvenient rather than dangerous. A jacket that lost 40–60% of insulation when wet was still acceptable if the wearer could return to warmth within minutes or hours. This shifted design priorities. Clothing was optimized for lightness, appearance, initial comfort, and low production cost, not for long-duration thermal stability in wet-cold cycles. Durability, repairability, and moisture tolerance became secondary concerns. If a garment failed, it could be replaced cheaply rather than mended with sinew. Mountain men transitioned from buckskin as cloth became available at rendezvous. By the late fur trade era, 1,830 seconds, 1,840 seconds. Wool blanket capotes and factory shirts supplemented or replaced leather. The system no longer had to fail slowly. Knowledge followed incentives. As industrial production expanded and the frontier closed, traditional tanning skills faded. Trade schools and apprenticeships stopped teaching fiber behavior and material physics rooted in survival. Use brain tanning. Never industrialized successfully due to its labor demands. Buckskin moved from essential technology to cultural artifact. What had once been practical engineering became costume or niche craft. The same pattern appeared elsewhere. Housing construction prioritized speed over thermal mass, stick frame homes over log cabins. Heating systems assumed uninterrupted fuel supply. Tools favored specialization over resilience. In each case, systems that depended on constant energy input replaced systems designed to buffer failure. Buckskin didn't lose to better performance. It lost to a world where sustained performance mattered less. Once warmth could be purchased cheaply and instantly through factory garments and fossil-fueled heat, the cost of inefficiency disappeared from daily life. Clothing no longer had to cooperate with the body under prolonged uncertainty. It only had to work long enough to reach shelter. That shift explains why buckskin vanished so quickly after the 1,840 fur trade decline, and why its advantages are now being rediscovered only at the edges. Among modern bushcrafters, reenactors, and outdoor enthusiasts who seek gear for off-grid winters or multi-day immersion, where energy remains limited and failure still carries real consequences. Buckskin clothing didn't work because frontier people were tougher, wiser, or more adapted by nature. It worked because it was built around constraints that couldn't be ignored. Frontier systems assumed cold would be sustained, moisture unavoidable, and failure unacceptable. Clothing had to remain functional while wet, compressed, exposed to fire, and worn continuously through cycles of exertion and rest. Buckskin met those requirements because it respected how heat, vapor, and materials actually behave in the real world. Modern cold-weather clothing often solves a different problem. It is optimized for short exposure, controlled environments, and rapid retreat to warmth. It performs well as long as energy, shelter, and predictability remain available. When those assumptions break, when moisture accumulates internally, when drying isn't immediate, when movement stops, the system degrades quickly. This isn't an argument to abandon modern materials or return to the 19th century. It's a reminder that thermal performance is not about peak insulation ratings or technical claims. It's about how a system behaves when conditions stop cooperating. Frontier buckskin systems failed slowly. Modern systems often fail suddenly. The lesson isn't what to wear, it's how to think. Systems that endure tolerate moisture, allow adjustment, and remain functional under abuse. They trade maximum efficiency for predictability. They work with human physiology instead of demanding ideal behavior from it. That logic kept people alive in Subzero winters, long before modern jackets existed, and it still applies anywhere. Warmth depends not on convenience, but on resilience.